Welcome, and thank you all for being here. Today, we are embarking on a journey into the evolving landscape of software development with a presentation titled Taming the Genie: Experiments in Augmented Coding and the Future of Software Design. This session is based on the insightful experiments of Kent Beck, a pioneer in software engineering. As we witness the rapid integration of artificial intelligence into our daily workflows, we must ask ourselves how we can best harness this powerful genie to enhance our craft. Join me as we explore how augmented coding is reshaping the way we think about, design, and build software for the future. We are currently in what we call the horseless carriage stage of coding. This concept highlights how we initially absorb technological innovation by filtering it through our existing mental frames. Historically, we tend to translate old habits into new technology before we can truly appreciate the fundamental changes that technology enables. Looking at the evolution of communication, the wireless telegraph was initially understood as exactly that, a telegraph without wires, before it matured into the transformative medium of radio. Similarly, electronic mail was first conceptualized as a digital version of physical letters before evolving into the ubiquitous messaging systems we use today. Even the early horseless carriage was designed to look like a carriage without a horse before the industry realized the full potential of the modern automobile. Today, we find ourselves in the LLM code generation phase. Currently, we are using large language models to replicate the way we have always written code. However, we have not yet identified what the final, native form of this technology will be. As noted in the key insight, this transition cannot be rushed. We must live with the technology and understand its second-order implications before we can find second gear and move beyond our current paradigms. The hypothesis we are exploring is code like me. Our primary goal was to achieve augmented coding, the ability to get an AI to produce code that isn't just functional, but reflects the high quality and craftsmanship of a seasoned expert. There is a common belief in the industry that assigning a specific persona to an AI prompt significantly improves the quality of the output. To test this, we conducted a near-zero-cost experiment aimed at validating the null hypothesis, the idea that appending a specific expert persona, such as Kent Beck as shown in our prompt terminal example, actually makes no measurable difference to the underlying structure of the generated code. We wanted to see if the AI truly shifts its architectural approach when told to emulate a specific pioneer of the field, or if the results remain largely unchanged. The rope data structure offers a powerful solution for the challenge of efficiently deleting a character from an exceptionally long string. In a naive approach using a standard string array, a single deletion results in an O of n cost. This requires shifting every character following the deletion point, which can involve moving millions of characters for large datasets. In contrast, the rope tree approach achieves this in constant time. Instead of shifting data, it restructures the tree by allocating just 3 objects per delete operation. By representing substrings as nodes in a tree, we move from a costly linear operation to a highly efficient, constant-time process, regardless of the string's overall length. In Phase 1, we focus on establishing a persona using the specific prompt, code like Kent Beck. When evaluating the results, we observed several positive shifts in coding style. Variable names became significantly more descriptive, and the testing strategy shifted toward modular, isolated unit tests, reflecting a TDD-oriented approach. Overall, the code felt more professional and polished. However, there were notable drawbacks regarding the structural output. The model still implemented a standard binary tree and completely ignored the composite pattern typically used by the real expert. Ultimately, while the persona influenced the stylistic how of the implementation, it failed to change the fundamental what of the underlying architecture. In Phase 2, we move into providing specific design guidance and constraints to shape the output. By using a prompt such as use composite pattern and break behavior into small classes, we direct the AI toward a more structured architecture. As illustrated, the initial output, which might have been truncated or overly verbose, is passed through this constraint injection process. This layer of explicit instruction forces the model to organize its logic into distinct, manageable components, like the substring and concatenation classes shown here. The result is a finer-grained design that adheres to clean coding principles. Remarkably, the AI solution in this instance was actually simpler than the original human plan. By utilizing substring ranges from 0 to size, it avoided the need for more complex null objects. This shows that well-defined constraints can lead to more elegant and efficient software designs. In Phase 3, we conducted the cross-product experiment. To isolate specific variables, 4 distinct groups were tested against the rope problem. The first group is our control, representing the standard assistant. The second group, labeled Kent Beck, utilizes the persona only. The third group, titled Composite, applies constraints only. Finally, the combined group integrates both persona and constraints to evaluate their collective impact. Our findings are summarized here in this matrix of effects, which categorizes the results based on 2 dimensions: micro-behavior impact, or style, and architecture impact, which represents the macro-level structure. Starting in the bottom left quadrant, we have our control group, which establishes the baseline performance for the study. Moving to the top left, the persona-only approach demonstrates a high impact on micro-behaviors. This leads to good test-driven development habits and better naming conventions, though the overall system architecture remains standard. Conversely, in the bottom right, the constraints-only approach yields a significant macro-level impact by producing the correct class hierarchy, even if the coding style remains verbose or standard. The clear winner is the combined approach in the top right quadrant. By pairing both personas and constraints, we achieve the optimal result: the right composite architecture combined with the right TDD habits. This leads us to our key conclusion. Personas drive micro-behavior, while constraints are the essential lever for driving macro architecture. The concept of encoding expertise highlights a common trap in how we interact with artificial intelligence today. Meticulous prompting is often an attempt to manually encode our own human style and logic into the machine. In doing so, we risk micromanaging the output rather than leveraging the immense scale of the tool at our disposal. This perspective is supported by The Bitter Lesson, a seminal paper by Rich Sutton. Looking back at 70 years of AI history, there is a clear and consistent pattern. Approaches that leverage computation yield far superior results compared to those that attempt to formalize human expertise. As illustrated here, while human intuition has its place, it is the scalability of compute that truly tips the scales. Progress in AI has historically been driven by general methods that can effectively use increasing computational power, rather than by the cleverness of human-designed rules. The shift depicted here represents a fundamental transition in how we interact with and utilize artificial intelligence, moving from a paradigm of direction to one of selection. In our current environment, we rely primarily on prompt engineering, a one-to-one relationship where a human must carefully guide a single AI agent to achieve a specific result. In this model, the quality of the output is often bottlenecked by the precision of human instruction. As we look toward the future, we are moving into a paradigm defined by compute scaling. Instead of one human directing one agent, we will leverage massive computational power to deploy millions of agents working independently. This approach mirrors evolution by selection. Rather than attempting to craft one perfect result through manual direction, we generate a vast multitude of candidate solutions and then use automated selection processes to identify the best outcome. We are not limited by the individual capabilities of a single model. Instead, we use scale to generate, evaluate, and ultimately select the highest quality results. The design contest represents a fundamental shift in how we approach automated development, moving from manual craftsmanship to high-scale iteration. As Jessica Kerr insightfully noted, we are not truly wasting code. Instead, we are using volume to discover excellence. The process begins in the generate phase, where we create upwards of 1 million variants. This allows for an exhaustive exploration of the entire design space. We then move to the select phase, using a funnel to filter these variants based on objective efficiency metrics, specifically looking for the lowest cost in terms of time, tokens, and electricity consumption. Finally, in the integrate phase, we merge the most successful features from these top-performing candidates into a cohesive final solution. This workflow ensures that while millions of paths are explored, only the most effective architectural elements are retained for the final implementation. We are currently navigating the horseless carriage phase of artificial intelligence. Just as the first automobiles were designed to resemble horse-drawn carriages, we are presently using prompts to mimic human experts, relying on familiar professional frameworks to guide model outputs. Through this process, we have learned a fundamental lesson.
Personas are highly effective at refining style, while constraints are essential for improving structure. When these two components are combined, they yield the most sophisticated and reliable results. As we look toward the future, the objective is to move beyond the manual encoding of style. Instead, we must begin leveraging raw computation to drive performance. The shift is clear. Our focus should transition from designing the perfect prompt to designing the perfect contest, establishing the frameworks and evaluation metrics that allow computation to arrive at the optimal solution.
Taming the Genie explores the intersection of disciplined software craft and the raw power of modern computation. This presentation synthesizes insights from Kent Beck's Piety First and Rich Sutton's The Bitter Lesson to examine how we manage complexity in an era of rapidly scaling technology. By applying the design philosophies found in Beck's writings, we can better understand the balance between human-driven structural improvements and the immense potential of general-purpose methods.